Welcome back. So today's lesson is chapter 13, the atmosphere in motion. So we have looked at the atmosphere in the vertical, kind of taking a look at its structure based on temperature and pressure. We did that in chapter 11. In chapter 12, we looked at the role of water vapor, and then of course the condensation of that and the various types of precipitation. And so now we want to look at another very important element of weather, the pressure. And so atmospheric pressure is really behind the motion of the atmosphere in the horizontal. Of course, as well as in the vertical. So we have a three-dimensional atmosphere. It is continuously in motion, as we are going to see here, many forces kind of being applied to create that motion. So atmospheric pressure, as we mentioned before, is the force exerted by the weight of the air, that mixture of gases of the air from above, and that presses down by gravity at the Earth's surface. And so the weight of the air at sea level, we mentioned, at sea level, right? So where you've got your greatest pressure is 14.7 pounds per square inch, if you remember that, PSI. 1 kilogram per square centimeter, if you need that in the metric units. We also, we introduced a unit that is used, meteorologists really do use this one in particular, a unit of measurement, the millibar, abbreviated MB. So there's like 1,000 millibars in one bar. So a millibar, standard sea level pressure is 1013.2 millibars, so just over that 1,000 millibars at sea level. And so you will see millibars used quite a bit. But definitely we learned in the vertical profile that air pressure decreases with increasing altitude. So as you went up in the atmosphere, there's less and less kind of accumulation of your air molecules, and so that creates less and less pressure as you go up in altitude. So in elevation, you do get a decrease in air pressure. And of course, these variations of air pressure are going to be what is the principal driving force of the motion of our winds, having variations in air pressure. And there is a gradient with our air pressure, just like there was with our temperatures, always going from high, regions of high towards low, high temperature to low temperature. Recall our gradients on our topographic maps for those of you in labs, with our stream gradients, right? High elevation to low elevation, we had a gradient. You're going to see many gradients, and so this is yet another gradient. Goes from high pressure to low pressure. That would be your direction. And so of course variations of air pressure across Earth's surface is what that principal driving force of the cause of our winds, right? The motion of the atmosphere. We certainly do have some instruments that we measure our air pressure with, our atmospheric pressure. So we mentioned the millibar. Also, we use inches of mercury mainly for, English units, but standard sea level pressure is almost at 30 inches of mercury. And so 29.92 inches in particular of mercury. And you think, well, why mercury? What's going on with that? Well, we have what we call a barometer, so a bar, right, for millibar, bars, that will measure the pressure. So it's an instrument, a barometer. Now, before they even figured out the mercury barometer, they used to use water as their barometer. But the mercury barometer in particular was invented by Torricelli in 1643, so quite a while ago, 1643. But basically he started out with a sort of a basin of water and sort of this inverted tube. I've got a kind of a drawing here, and I think they'll show one, but I want to kind of compare the water version with the mercury version. So here's the water versus the mercury barometer. So they had this dish, right? Here's the water one. So just sort of a dish with water, and then this inverted tube. So they had a tube, an inverted tube. And depending on what your atmospheric pressure was, it would cause the water, you know, the more pressure on the water, that would cause water to rise up into that inverted tube, right? That evacuated kind of inverted tube there. Well, with water, it was very cumbersome because sort of atmospheric pressure in there would have been 33 feet of water. Imagine 33 feet. Let me grab a yardstick here, or a meter stick here. 33 feet. So there's just, you know, a little over 3 feet here in a yardstick. Imagine you would need, you know, 11 of these. That is so tall. Very, very cumbersome with the water. But water is, you know, not very dense. It's at about 1 gram per centimeter cubed. So Torricelli got to thinking, well, what could I use? What liquid could I use that was much more dense, and so that it didn't have to rise so high up into the tube? And so he come up with and arrived with the mercury. The use of mercury, liquid mercury, is about 13 grams per centimeter cube. So you could kind of reduce the height of your tube by a factor of 13. And so it would end up being closer to 30 inches of mercury versus, you know, 33 feet of the water. So that's extremely cumbersome. But so he did develop the mercury. Well, we all know that liquid mercury is not good for you. It's quite dangerous. But you'll still see these. So it was 30 inches in, you know, so 29.92 inches, 30 inches, we'll say, of mercury versus then the 33 feet of water. So the less cumbersome one certainly was the mercury barometer. And we do have one of these. The chemistry lab uses this, but it's a glass tube that will, you know, the mercury will rise and fall depending on the air pressure. So many in either inches of mercury, a lot of times they'll talk about, you'll see that, or centimeters of mercury as well. So you use a glass tube filled with mercury, and it will go up or down depending on the air pressure, just how much weight is pressing down on your mercury, right? And that'll cause it to rise into the tube. And up in there, they're saying 76 centimeters if we want that in centimeters, or 29.92 inches of mercury. Sort of that's kind of standard sea level atmospheric pressure. Okay, with a mercury barometer is one that we can use. But again, mercury, you know, this will measure the atmospheric pressure, then a barometer here, but mercury, quite dangerous, poisonous liquid. The vapors are poisonous as well. Plus, you know, as far as being portable, that's not really very portable. You pretty much got to stick that on your wall and leave it put. But Torricelli was noticing that as he had his mercury barometer set out, day after day he would notice changes in air pressure, and he was correlating those changes in air pressure with what was going on with the weather. So anytime he had this low kind of air pressure coming in, he could kind of predict that, oh, this means I'm about to get some stormy weather. Okay, the low pressure did. And then when he had high pressure a few days later, high pressure would kind of come over, and he noticed that, oh, the weather was fair weather now. So a high pressure system does tend to favor the fair weather, and a low pressure system favors stormy weather. And so in a sense, he could kind of predict what the weather was going to do based on his atmospheric pressure trends. Was the pressure rising? Was the pressure sinking or falling, they would say. And so he could do that and kind of predict what weather systems were coming. So this was very beginnings of the meteorological forecast kind of thing. He also noticed that, and again, this is very cumbersome, but he could take his mercury barometer and go up in elevation, go to mountainous terrain. It's quite difficult, right, with that mercury sloshing around, but he noticed that when he went up in elevation, so up in altitude, up a mountain, the pressure got lower, right? So he was even able to realize that pressure does decrease with altitude, right? So Torricelli was the first to kind of come up with our barometer there. So yes, the mercury barometer is not very transportable, inconvenient because of the liquid, and the mercury, of course, is bad news if that should break kind of thing. So they came up with an aneroid barometer. This one doesn't have any liquid, so this is without liquid. It uses sort of almost like a serrated kind of accordion style of some metal chambers that will, contract and expand according to what was happening to the air pressure. So these aneroid barometers uses an expanding chamber, right? And it's connected and hooked up to a barograph, which can continuously, with a little needle, kind of continuously record the air pressure. So this little aneroid barometer can also be used too, because we were able to determine that the air pressure does decrease with altitude or with elevation. They kind of use one that's called an altimeter, altitude meter, an altimeter. So I don't know how well you can read that, but an altimeter, A-L-T-I-M-E-T-E-R. So an altimeter is basically a barometer that measures elevation based on the pressure changes with altitude. So it uses that little aneroid type of a barometer in there, the little evacuated kind of chamber, metal chambers in there that can expand and contract. But that will also let them know, based on air pressure, what the altitude is. This is very useful in aviation. Pilots will use this. They need to know their altitude above, sea level to go through, mountainous terrain. They need to know their altitude. And so an altimeter can actually tell you what your height is based on air pressure. So that's an altimeter, and we certainly can use those barometers to figure out basically what the altitude is as well. That's an aneroid type of barometer. I think they have a picture of that too. All right, so there's the little chambers, the aneroid barometer, kind of like an accordion, but it is sort of like a metal can kind of thing, metal chambers in there, kind of hooked to, depending on, the expansion or the contraction of that, you'll get a pressure reading on the barograph, a little piece of paper, a drum of that's recording it continuously for you. That's an aneroid barometer. So a few ways that we can, measure the whether or not we've got increasing, rising pressure, decreasing pressure. So certainly on a weather report, a falling barometer, so your pressure is getting lower and lower. This would forecast the impending low pressure system, and low pressure systems certainly are stormy weather types of pressure systems. And why would that be? Because with a low pressure system, the air wants to rise, and when you get rising or lift in the atmosphere, as we saw before, that is going to cause the air to expand and cool, right? hit your dew point, your condensation level, precipitation can start to form at that. You get that saturation level. So a low pressure system does sort of indicate impending stormy weather. A rising barometer, on the other hand, would predict that we've got high pressure system coming our way. High pressure, remember, sinking air at the center of a high pressure. Anytime you have air that is sinking or descending, it's going to compressionally warm, and that is going to dry up your air, your moisture, right? The warming, it's going to reduce your relative humidity, dry up any possibility for clouds. So we do call that sort of our fair weather indicator of a high pressure system. So kind of looking at the trends of air pressure, say on a weather report, can help us to predict just kind of what the approaching weather is going to be. So very important element of weather is our air pressure. So factors affecting the wind. So remember, wind is basically gets its gradient due to variations in air pressure across the horizontal. So high pressure to low pressure, that's our gradient. That's the direction the wind is going to flow, from high pressure to low pressure. So that's one factor in affecting the wind direction, wind speed even. But this is always the direction that it will go in our gradient. Out of areas of high pressure toward low pressure. From high to low. Just keep that in mind in many of these gradients that we've been talking about. It's always from areas of high temperature, high elevation, high pressure to low pressure. Okay, that is the direction. Okay, the pressure gradient, we would call that. Pressure changes over horizontal kind of distance. A pressure gradient, and it is always from high to low. Keep that in mind. So pressure gradient is a very important factor, as well as, if you remember, we've mentioned the Coriolis effect. Wind is a fluid, just like our ocean circulation a fluid, and we are on a rotating platform, the Earth. And so you will get the Coriolis effect, which we will talk about. And another control of wind is friction. Friction is going to always operate opposite of the wind to slow the wind down. And it really only becomes important closer to the surface of the earth, where you have trees and buildings and that sort of thing, a roughness to your surface. Friction will become important. So these are the three main factors affecting our winds. The pressure gradient is first, the horizontal pressure gradient force, pressure change over distance, that's the gradient, and of course Coriolis and friction we'll talk about as well. But the first one here, our pressure gradient, let's back up a second here. When we do talk about gradients, if you recall our topographic maps, we have the contour lines. In the ocean, we had the those isotherms, the equal lines of equal temperature. And so we've got a new term in here called isobars. So bars, that unit that we use for pressure, are lines of equal air pressure. So isobars, these are like contour lines that they will draw out on an atmospheric map. And so anything along that one line will be an equal pressure. So we can set up sort of the pressure gradients in this method using our isobars. So we're going to take a look at the isobars here, lines of equal air pressure, and see how that looks on a weather map. Okay, and so here we have isobars on a weather map. Notice right off that we have a red colored L. That stands for the center of low pressure, okay, a pressure system. And then up over here, there's a blue H. So the H stands for a high pressure system, the center of the high pressure system on your map. So variations in pressure across a map region here is what this is depicting. So notice we do have lines, these little contour lines, these isobars. Anything along this line is 1024 millibars. Here's 1020, anything along this line, it actually continues up there, 1020. I know you probably can't see these too well, but you do have this PowerPoint. Here's a 1016 millibar, continues over here, 1016. And so as you go along, you can see anything along a particular line that's labeled is an isobar, an equal line of air pressure. And they typically will do a kind of a contour interval, an isobar interval of about 4 millibars. They usually do that. So you see the 1016, the 1020, the 1024. That's pretty typical on a weather map. And so that is showing you areas of course, over here, we definitely have we've got the center of the low pressure. It reads 996 millibars. The next line out, this is 1,000. Then we've got 1,004 millibars, anything along that line. 1,008, 1,012, that big one's the 1,016 millibars. And so you got that center of low pressure, and as you go outward, you get higher and higher pressure. So the lowest is at the center where the red L is. And so winds are going to want to go from high towards low. And so our wind directions are going to be toward that low pressure system, right? In a high, right, you're already in the high at the center with the blue H there, right up over here, center of high pressure. Those winds are going to want to go away from the high pressure system. And so we do see the winds going away from the high pressure system. And so these are isobars, and we can see these wind directions. They're showing us these little stick figures here that are a station plot. Kind of got something that can explain those just a little bit here, a station plot. This is something that comes from a meteorology book. But a sample station model plot. So the station, there are many, many stations that will be, of course, meteorologists are going to be reporting these elements of weather, you know, on a regular basis, because that's going to change moment by moment. So things like wind, okay, that's depicted by that little stick kind of figure there with some little feathers kind of coming off of it, sometimes a pennant. That's actually going to tell you your wind direction and your wind speed in that one little symbol there. The center here is the actual station, you know, whatever city you happen to be at, that's the station. So those winds are coming in, okay, into the station. And when you report a wind direction, you always report it from which the wind blows. Not where it's going, but from which the wind is blowing. So this would be sort of a north-northwest wind, right? With a speed of about 15. Okay, so each long feather, we would call it, the little stick, is 10 millibars. And so we've got one full feather and a half a feather, and a half a feather's 5 knots, I should say, for the wind speed. So we got 15 knots is our wind speed. 1 knot is approximately 1.15 miles per hour. So it's fairly close to 1 mile, a little bit off. We've got a temperature reading that would go here. Down below it, we have the dew point temperature. Remember, the dew point temperature is the temperature that air would need to cool down to in order to reach saturation, right? So very important to the meteorologist. There's all sorts of weather symbols here. The 3 dots are saying we have some moderate rain precipitation going on. Here's the sea level pressure. We've got the pressure trend. So is it rising? Is it falling? All very important things. what our sky cover is doing, so what our clouds are doing. All manner of weather elements are in this one station plot, but definitely the wind speed and wind direction are located on these little station plots. And so much information going into one little symbol here, but this is basically showing the wind. Here's one where we've got a pennant. The pennant, right, looks like a little triangle, a dark triangle. That would be 50 knots. So you have a pennant, you know, you got 50 knots. Say you add a long feather, right? You're going to be adding 10 to that. So 60 knots sort of thing. So we can figure out what our wind speed is and what our wind direction is by this little station plot symbols, kind of decoding those symbols. So what I'm seeing around my low pressure system is definitely, these are all going towards the low pressure. From high pressure out here towards low pressure would be my basic general direction, my pressure gradient direction of my station plots that are reporting. These are all trying to go in towards. And notice the spacing of our isobars, these contour lines. The closer spaced your isobars are, the faster the wind speeds are. So here, yeah, we got a pennant like 50 here. Here's 30 over here knots. There's 35. So those are really fast winds, closely spaced isobars, very fast-paced winds. Versus out over here on my high pressure, look how widely spaced those isobars are. That means you have slower winds. And just look at the symbols there. We have like a half of a feather, right? So 5 on that. Here, when you have the, kind of looks like a bullseye right up there, you have calm winds. You don't have any wind. So around a high pressure, yeah, and widely spaced isobars means you have slow winds. Closely spaced isobars, fast winds. Right? So the spacing of the isobars can tell you something about the speed of your winds, just like on our topographic maps for those of you in lab. If you remember, the closer spaced the the contour lines were, those equal lines of elevation were, that meant you had a steeper gradient, right? Well, this is a steeper gradient as well, which will make your winds faster. So this is a little bit of what that would look like on a weather map, but just kind of keeping in mind the spacing of the isobars are going to tell you something about your wind speed as well. All right, so areas of high to areas of low. Your isobars are equal lines of air pressure, and very strong winds are going to be seen if you have the presence of closely spaced isobars. Slower winds if they're more widely spaced, maybe even have calm winds in that situation. So this is your pressure gradient. That is definitely one factor, right? Always high to low. That is going to be controlling your winds, this motion of the atmosphere. Second factor, as we alluded to a little bit earlier, was the Coriolis effect. This is due to the rotation of the Earth. We mentioned this with our kind of surface ocean circulation as well, because of course the ocean circulation, surface circulation anyway, is driven by the wind. The wind was the principal mechanism for our surface currents. So air is a fluid, right? Just like the ocean currents. And so here we have a rotating platform, right? The Earth is rotating. And here we have the atmosphere moving on a rotating surface. And so you are going to get a deflection in the wind direction due to Earth's rotation. And there is sort of an opposite thing going on in each hemisphere. Let's see if I can find that picture I had from before. Here we go. So you've got your rotating platform, which is the Earth, right? And so the equator is much wider in diameter than the poles. And so in one day, let's say, the equator is not going to move quite as much in one day as the poles are. right? They're going to have to move a lot more than that wider diameter of the equator. And so this will have a kind of crucial impact on the wind directions. Right at the equator, as I mentioned, it's not really moving very much. You have zero Coriolis effect right at the equator, okay? But your poles, you have the fastest or the most of the rotation happening. So you have the most Coriolis effect being exhibited at your poles, your north and your south pole, as the Earth is rotating. But there is sort of an opposite in each hemisphere. So objects, say the wind, moving in the northern hemisphere tend to veer to the right, okay, of their direction, whatever their direction is, veer to the right due to the Coriolis effect. And in the southern hemisphere, veer to the left. And so there is sort of that opposite in our perspective of each hemisphere. But these will cause a veering, so a change in the direction of our wind. So we get that going. This has really become paramount in, of course, meteorology, oceanography, as well as ballistics, because imagine you're trying to hit a target, a missile on a target, and the Earth is rotating beneath that missile, okay? And so you've got to factor in the motion of the Earth, right? It is rotating, right? It takes 24 hours to make a complete rotation. But here you are trying to hit, a target with a missile going through the air, but the Earth is rotating. Your target's rotating. So you have to take into effect the Earth's rotation, right? If you're ever going to hit your target at all. So it will cause this deflection. The deflection is, just remember that, to the right in the northern hemisphere and to the left in the southern hemisphere. Okay, that's definitely going to be a factor. We'll come back to friction here in just a second. But let's look at that. So, yes, they're trying to hit a target here, right? Your target's here, but as the Earth is rotating, your target's moving out of the way. So you do have to factor that in if you're ever hoping to hit your target. Right, so your target's over here, but the Earth has rotated out from under there. So that's what they will do with ballistics. They'll factor in Earth's rotation. They can do a simple little calculation, say, okay, we gotta change things and factor in that the Earth is going to be moving beneath our missile as we go. So definitely it is going to cause it, whatever the direction your wind is, going to cause it to veer off to the right in the northern hemisphere and to the left in the southern hemisphere. I think I've got something here for us that can show that going many different directions here. There's our Coriolis effect, deflection to the right in the northern hemisphere. So say we've got a wind coming from the south, right? It's going this dashed line here. It's going to veer off to the right. Say we've got a westerly wind coming along. It's going to veer off to the right. We got a northerly wind coming this way, veering to the right. Easterly wind, veering to the right in the northern hemisphere. Opposite in the southern hemisphere. Here we have a northerly wind direction initially. It veers off to the left here. Here we've got a southerly wind veering to the left in the southern hemisphere. So there is an opposite in those hemispheres. This is going to give some circulation, some rotation to our wind. These become very important, the Coriolis effect, combining with our pressure gradient force to give us that rotation in the atmosphere, either clockwise or counterclockwise, really depending on our pressure system. So Coriolis effect, very important in affecting, a factor affecting the motion of the wind, the rotation of the wind. Okay. Deflection of the wind is due to the Coriolis effect, and it is strongest at the poles, right? Zero or absent at the equator. So keep that in mind. we will think about those deflections here. Before we go to that one, we want to look at friction. Okay, so friction, a third factor that does affect our winds. Friction again becomes important as you are more near the surface of the earth. So only important near the surface, and it will act to slow the air's movement. It is a vector that will act directly opposite of your wind direction by slowing the wind down. Okay, so friction is another vector that we would talk about, force vector, but only important towards the surface. Okay. So in looking at upper air winds versus winds at the surface, so they're talking here about the upper airs, upper airflow generally blows parallel to our isobars, and we're going to show a little diagram there. Remember our isobars, right? Equal lines of pressure. And they're saying that it will blow generally parallel to the isobars. So upper air winds basically have two vectors. They have the pressure gradient force, always going from high to low, and the Coriolis effect, always trying to veer things to the right in the northern hemisphere, to the left of your direction of flow in the southern hemisphere. So in a geostrophic wind, they will say that the pressure gradient force and the Coriolis effect are equal or balanced. So they're, going opposite of one another. They're balanced. The vectors are kind of balanced. And so you basically will get your wind direction, because of the balance of those two vectors, to blow parallel to the isobars. Okay? And these are really fast moving, kind of like a stream. They call it a jet stream, a river of air. Of course, air is like a fluid, like our streams, right? Swift moving, very fast, 120 to 240 kilometers per hour, a swift moving stream of air at very high altitude though. This is upper air flow that we would call the jet stream. And the jet stream really does steer. It's a steering mechanism for the weather systems that are coming through, those various high pressure and low pressure systems. It's really a steering mechanism for those. But that's known as geostrophic winds, upper high altitude winds. Basically, you just have your pressure gradient force, the horizontal pressure gradient force, and the Coriolis effect. Those two vectors, the resolution of those two vectors makes the winds go parallel to the isobars. Very fast moving jet stream. So here's a nice depiction of that. You've got your pressure gradient for one factor. We've got high pressure here, low pressure here. So it's always going to go from high towards low. So the red arrow is depicting your pressure gradient force, right? Your horizontal pressure gradient force is the red arrow. Here we had 912 millibars, 908, 904. Basically higher pressure towards lower pressure. That's going to be the direction of that force, the pressure gradient force, high to low, always. Okay, then Coriolis, the Coriolis effect comes into play. Remember, and we're looking at the northern hemisphere because this is the United States on the ground map down here. We're looking at the United States here. But up above, right, the upper level wind, that Coriolis force is the black arrow. And so that's always going to want to veer your wind towards the right. And so once we get the resolution of the pressure gradient force and the Coriolis force, this black arrow and the red arrow, pressure gradient's the red arrow, black arrow is the Coriolis force. Those oppose one another when it's resolved. And the wind direction, though, goes, as you can see, parallel to our isobars. That's what they were talking about. This is called the geostrophic wind. Geostrophic wind. Winds are going to go parallel to the isobars, and it's really the resolution of those two vectors horizontal pressure gradient force and Coriolis force, making the winds go parallel to your isobars. This is upper level winds, right? Now looking at the surface level winds, okay, so here's kind of that first one, the upper level. No friction is in the mix here. You got your Coriolis force and your pressure gradient force being opposed or balanced, okay? And your wind direction goes parallel to the isobars. Well, we got to throw in friction as we get towards the surface. So friction, as I mentioned before, is always going to act opposite of your wind direction. It's going to try to slow your winds down just a little bit. So again, pressure gradient force is doing this. Friction's trying to go opposite your wind. So it will change just a little bit, okay, to the point that your wind direction now will go across isobars toward low pressure. Okay, so it goes across. See how these are going parallel to the isobars? We cross the isobars as we add the friction in. Resolution of those vectors causes the wind to go across isobars, but still always toward low pressure. We start to get a rotation around a pressure system in this manner. Okay, and so we'll look at some of those in a bit. Some terms for us though for these pressure systems. High pressure versus a low pressure system. What is that flow of the wind going to be around these pressure systems is what we'll be looking at in this next segment here. So we have some terms that you'll want to make sure you can relate these two, highs versus low, but we have some names for those. A cyclone is a low pressure system, okay? There are some opposites as far as what's going on hemisphere-wise, but we'll tend to think about the northern hemisphere, and that's where all our weather concerns are, in the northern hemisphere. But know that there are some differences because of the Coriolis effect in the southern hemisphere. But a cyclone is a low pressure system. Keep that in mind. Now, of course, pressure is lowest at the center, so pressure decreases towards the center. Now, what's going on with your winds associated with a cyclone or low pressure system? We want to look at what's happening in the horizontal as well as in the vertical, because we got a three-dimensional atmosphere, right? So what's happening, again, northern hemisphere, of course, you're going to get a convergence of your winds toward that low pressure system. Convergence, meaning going towards the low pressure, right? That's our gradient from high toward low. So all your winds are going to converge, we would say. Convergence, going inward. So they're going to converge, but then what's going to happen? It's going to go in a counterclockwise motion. Kind of show you that. And they'll be showing this as well, but this is a low, well, put it right here, baby. I don't know how well that's going to show for us, but we got a low pressure system. Now remember, that gradient's always going to cause the winds, whatever direction they're coming, to go towards the center. Coriolis effect in the northern hemisphere is going to want to make those veer off to the right of their direction. So we got a wind coming this way, pressure gradient force, and Coriolis effect is going to make that kind of go in a to right direction. Here we got a southerly flowing wind coming in, pressure gradient veers to the right. So what ends up happening, we get this counterclockwise and convergence. So counterclockwise around the low and toward the center. So inward or convergent. Convergent and counterclockwise in the northern hemisphere, right? Resolution of pressure gradient and Coriolis effect around a low pressure system. Okay, so inward and counterclockwise around a low. Do keep those kind of in mind of what's happening. Southern hemisphere, okay, your pressure gradient is the same. high to low. So it is going to still be convergent. But however, in the southern hemisphere, remember everything's veering to the left, so that's going to cause a clockwise motion around a low pressure system in the southern hemisphere. Okay, that's what's going on with that one. Okay. But in the northern hemisphere, that's where we are. That's a cyclone, and certainly towards the center, right, inward, convergent, and counterclockwise happening. We'll be looking at in the vertical as well. Low pressure is going to have some rising air. You've got low pressure at the center. That's going to allow the air to rise. It's less dense, right? Low pressure, less dense. Rising in the atmosphere, expanding and cooling, right? So that's why it's often going to bring you the clouds and the precipitation, right? That rising air, adiabatically cooling, expanding and cooling. You reach your dew point, saturation point, condensation can start to happen. You're going to create the clouds and the precipitation. It's kind of like our stormy weather prediction is a cyclone. It's low pressure system. So it is associated with rising air, low pressure at the center, right? Winds are like converging at the surface, rising air, and it's all going in a counterclockwise motion, okay? That is going to bring you your clouds and precipitation. So that's horizontal and vertical, three-dimensional motion, okay? Opposite of this is an anticyclone. So it's not a cyclone, it's an anticyclone. This is a high pressure system, highest pressure at the center, of course, and then that decreases as you go outward. So a center of high pressure is known as an anticyclone. Pressure, of course, has increased its highest at the center and sort of decreases outward. So imagine what your winds are going to do if you have the high pressure at the center. Pressure gradient is right from high to low. So those winds are going to be going outward, which we call divergent. They're going to be diverging from the center. Okay, as you have that high pressure air sinking, it's very heavy, very dense, it's sinking. The winds are going to be going away from the center of the high pressure. And then let's look at what happens to the wind directions as far as rotation around the high pressure center. And think about the northern hemisphere here. Of course, always going to be divergent because high to low. High pressure is going to be moving outward, so diverging, that would be one of the directions. And it's going to go clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. Let's take a look at what's happening. The Coriolis affected pressure gradient. On our high pressure, so I have an H here depicting the high pressure, right? Highest pressure at the center. So of course the pressure gradient force, my little dash line, is going to be taking the winds away from that center of high pressure, high to low, right? So winds are going to go from high towards low out here. That's your pressure gradient force, right? Any which direction we want to go. Well, in the northern hemisphere, right, that wants to veer. The Coriolis effect wants to veer everything to the right, so that would go this way. That would get veered that way, to the right, giving us a clockwise flow. Think of your clock, right? Clockwise flow about a high pressure center. So it's divergent and clockwise, okay, in the northern hemisphere. Okay, it's still divergent in the southern hemisphere, but of course it's counterclockwise because everything's veering to the left in the southern hemisphere. So think of the northern hemisphere for a high pressure, divergent away from the high pressure center, and clockwise for the rotation about that. And also high pressure, very dense air, sinking air. You get sinking air, what happens? Adiabatically, you get compressional warming, right? As the air pressure gets greater, as you get towards the surface of the earth, increases, right? Friction happens, right? And you start getting warming, compressional warming. The subsiding air, sinking air, subsiding air, that is going to, right, reduce your relative humidity. That's going to dry up any clouds, chance for a cloud, right? So no precipitation. So yeah, your high pressure systems are usually our fair weathered friends, right? They bring fair weather. So an anticyclone, think of fair weather for that. So air is subsiding in the center of an anticyclone. But again, divergent and clockwise in the northern hemisphere. So here we've got them side by side, and they really do follow one another, right? You got an area of high pressure here, area of low pressure here, area high pressure, area low pressure. They follow one another. And typically here in the United States, we've got a map of the United States here, the jet stream is going to steer our high pressure and low pressure systems, our anticyclones and cyclones from the west toward the east. That's sort of the direction of the westerlies, the prevalent wind directions across the United States. It's going to cause those to trek from the west to the east across the United States. So when we're trying to figure out what the forecast of our weather is going to be here in Arkansas, we always kind of look to the west and see what's coming. Are we getting a high pressure system, or are we getting a low pressure system coming our ways? And it takes several days for these to kind of trek across the United States. But these are our cyclonic and anticyclonic winds. So again, to reiterate, around the low pressure system, your cyclone, you are getting convergent winds. They are coming towards the center. You can see all these winds coming towards the center. And in the northern hemisphere, this will be a counterclockwise motion. So counterclockwise, you see all your winds, right? They're crossing the isobars going towards the low pressure center, high to low pressure gradient, and the Coriolis effect gives us our rotation counterclockwise about the cyclone. Opposite on the high here, you've got the high pressure in the center, so all your winds are going to be diverging. They're going to be going away from. You can see them going away from. But notice how they are going clockwise around that, right? Everything's getting veered to the right of the direction there. So you see the clockwise rotation and the divergence of the winds. So this is together. This has got the pressure gradient, right? Horizontal pressure gradient, high to low, and the Coriolis effect. Northern hemisphere veering everything to the right of the direction of the wind flow. So, right? Counterclockwise and inward, or convergent, we call that. And clockwise and divergent, or outward, for your anticyclone. High pressure sinking at the center there, fair weather. Low pressure, air rising. You're going to get your stormy weather with that, your clouds and your precipitation with a low pressure or cyclonic system. So try to keep those two straight, maybe review that, and really look at all the vectors that are coming into play that are causing that rotation of the air, the movement or the motion of the air. And these are very important systems there. And here we've got it in the three-dimensional, pulling that all together for us. So at the surface, you do have a low pressure system, right? So you are going to get the convergence, high to low, going towards the low pressure system. You are getting the counterclockwise flow because of the Coriolis effect, but that low pressure is going to be causing the rising from the surface, rising. Of course, the air is going to diverge aloft. It's going to have to go somewhere, and it'll spread out, right? And it'll actually feed into the high pressure system, right? You've got here high pressure at the surface, diverging winds. When you have diverging winds, right, the air is going to sink. It's going to be pulling in the air from aloft, right? Convergence aloft, causing subsiding air here, high pressure there. We're going divergent and clockwise. So try to put that all together three-dimensionally. Horizontal motion as well as vertical motion in the atmosphere. We've got tremendous amount of circulation happening in our atmosphere, and it's really driving our weather systems, right? Low pressure, you're going to get the stormy weather. High pressure, you're going to get the fair weather, the drier and the fair weather. So really does control our weather scenarios that we're going to have. So general atmospheric circulation, with our understanding now of this high pressure system, low pressure system, circulation, keep that firmly in mind as we think about this. We're going to look at the general atmospheric circulation as a whole. So we do have some, high pressure, kind of semi-permanent high pressure systems, kind of semi-permanent low pressure systems globally. So let's think about this globally. The general atmospheric circulation. Of course, the underlying cause of this variation of the high pressure, low pressure is unequal surface heating. So remembering that Earth, yes, is tilted on its axis and right, that rotates this way, and it revolves around the sun at the center there, right? So we've got that, sometimes we've got direct heating in the southern hemisphere, sometimes we get the direct heating in the northern hemisphere, our winter, summer solstices, as we talked about before, but that will cause kind of this unequal heating of the surface. We also mentioned land likes to heat up faster into higher temperatures and cool down to lower and really, lowest temperatures over land versus water. That differential heating of land versus water. Water's kind of moderating effect. Land will heat up, really fast and to higher temperatures than water and cool down as well. Unequal heating of the Earth's surface. So bringing that kind of together, we do get sort of an idealized circulation here. So on the rotating Earth, there's basically 3 pairs. I might venture to say there's 4 pairs of atmospheric cells that redistribute this difference in heat, right? Kind of over the equator, straddling, maybe 30 degrees, at least to 23.5 degrees north and south of the equator. Remember how we get really high sun angles there? So you get very warm temperatures around the equator, and again, the poles, right? Remember how sometimes you get, 24 hours of darkness at the poles or 24 hours of daylight at the poles, so real extremes there. So you tend to get cooler temperatures at your poles, warmer temperatures around kind of straddling the equator there. So definitely unequal heating of that. But we have these pairs of atmospheric cells, they're called Hadley cells, that will help to redistribute kind of that heat. And again, a therm is always from high to low heat as well. So we're trying to get all that excess heat in the equator area towards the poles, and then vice versa kind of thing. So an idealized global circulation. They're going to talk about several different cells here. An equatorial low pressure system. So again, near the equator, very high sun angles, we get our higher temperatures, right? Warmer air is going to want to rise, it's less dense, so it will rise. So we get this low pressure system there, the equatorial low pressure system, pressure zone. Rising air, you sort of get this discontinuous band of precipitation or thunderstorms along the equator. So abundant precipitation that we'll find along and through there. Okay. So, and that's known as the equatorial low pressure system, a pressure zone near the equator, and it is associated with rising air, so a low pressure in there. Let's see if I can get this to come off of there. It's a little drawing I have. I don't know how well you're going to see this. You may not see it too well at all. We'll see. But along the equator, 0 degrees latitude, and then I'm going to go to the northern hemisphere. Of course, this does happen in the southern hemisphere, like a mirror image kind of thing. But we have the equatorial low Okay, again, a low pressure system, northern hemisphere, right? This is going to go in a counterclockwise direction in there. Okay, well, in looking at that then, all that rising air is eventually going to diverge at the top, get to cooler temperatures, and it will begin sinking, right? The air will become more dense and it will begin sinking a little further up. So near about 30 degrees latitude, and we mentioned these before, you're going to get the subsiding air. And as that air is sinking, compressional warming, that's going to dry things out. So it's very stable, dry air. This is in a location we call the subtropical high pressure zone. We've mentioned the subtropical high pressure zone when we talked about our deserts. And remembering, I kept saying, we'll talk about this later, about the sinking air. This is a high pressure cell in this region. Here's our world map, kind of color coded, showing you our desert regions. So here we're at about 30 degrees, right? North latitude in this case. It also happens south latitude as well. It's like a mirror image of these cells. But this would be the subtropical high region, an area of sinking pressure. Notice how we are seeing the major deserts, these browns and yellows, kind of orangey colors, very dry regions because of the sinking air, right? You also see it in the southern hemisphere along through here, our great deserts and steppes, right? Dry regions because of the sinking air. That's known as a subtropical high. So along about 30 degrees, we're just going northern hemisphere here, we have a high pressure system, the subtropical high, right? So you've got the clockwise motion around your high pressure system. So we have the equatorial low going counterclockwise, the subtropical high going clockwise. The convergence of the subtropical high winds and the equatorial low winds give us these winds we call the trade winds. Okay, the trade winds, and they are an easterly wind. The trade winds. The reason we call them the trade winds is because old-timey, back when we used to do a lot of sailboat ships, those big ships that would do a lot of trades. You've got, up here in England, they're trying to come over to the New World and trade their goods. Well, they will pick up on the easterlies, right? Those easterlies are coming from the east, and that will bring them right towards the New World so that they could do all their trading, right? And so those were known as the trade winds in there. Okay, but that's a high, right? Stable, dry air, sinking air. These are the location of the great deserts, as I mentioned. Air traveling equatorward from the subtropical high, right? The kind of the confluence of that creates those trade winds, we call them, right? So your trade winds are the surface winds between the subtropical high and the equatorial low. That creates your trade winds. Well, if we take a look, we've got the subtropic highs. We've got another one. They're going to mention these westerlies here, but let's put that one in. If you go up to about 60 degrees, okay, north latitude, of course, you've got another low pressure system. They like follow one another. The low pressure system called the subpolar low at about 60 degrees. There's a low pressure cell across there. Well, the confluence of the subtropical highs going clockwise and this subpolar low going counterclockwise creates what we call the westerlies. Of course, they're coming from the west and going to the east. Those are known as the westerlies or the westerly winds. The westerlies, these winds are the ones that really will dominate the flow of our pressure systems across the United States, because we are kind of right in there, right? This is 30 degrees north, this is 60 degrees north, so mid-latitude is about 40 degrees north latitude. So this will be what really drives our weather systems across the United States. from the west towards the east. So the westerlies become very important factor in our weather systems and weather patterns that we get. So air traveling poleward from the subtropical high, right, is going to give us the westerlies in there. So between the subtropical high and the subpolar low, those pressure zones, you're getting the westerlies. Okay, and so here they're talking about the subpolar low. That's at about 60 degrees north, of course 60 degrees south as well. Sort of a mirror image there. You're getting warm and cool winds to interact, right? Subtropical highs, subpolar lows, polars are cold, subtropicals warm. You are getting contrasting air masses, and we're kind of in a confluence of those contrasting air masses here in the United States. So when you get contrasting kind of different air masses coming together like that, you can get a clash, right? Cold air more dense, warm air is going to want to ride up over it. You're going to get frontal wedging, right? And so that can cause lift in the atmosphere, and our weather systems, our frontal kind of weather systems that we do get along here. So the polar front, an area of storms. A front is a boundary between contrasting air masses, warm, say, versus cold. Polar front. We get a lot of that. Then if you go on up to 90 degrees, so we're kind of going up here, there was 60 with the subpolar low. Go up to 90 degrees, you've got your polar high again, right? So we're kind of repeating low, high pressure up there. We've got very cold air that is, very high pressure, sinking air, very dense. So that's known as the polar high. And of course the confluence between subpolar low and polar high, right? There's your low going that way. There's your high going that way. We have what we call the polar easterlies way up there. So some wind bands happening along there. The polar easterly. So polar high pressure zone, cold subsiding air, air spreads equatorward. That's those polar easterly winds. The polar easterlies always collide with those westerlies along what we call that polar front. That polar front, yeah, that's kind of what does dictate a lot of our weather. Very strong clashes between warm and cold air. A polar front, yeah. A lot of times that's something that can affect our weather systems as well. Okay, so these are the main kind of cells. I think they're going to have a nice culmination diagram of all of those. There it is, the idealized global circulation. And on there straight, somewhat. Again, a mirror image of these as you straddle the equator, north and south, right? So here we are, the equatorial low right at the equator, a low pressure system, lots of solar radiation along the equator, right? High sun angles, warm temperatures. You're going to get rising air out of that, very less dense, buoyant air. So that's why that air wants to rise in that location, discontinuous band of thunderstorms. It's also kind of why we get that region called the tropics, right? About 10 degrees north or south of the equator, all these pinks and salmon colors, right? Right up across, straddling the equator. Lots of rain there. That's our tropics region in through there. Lots of moisture happening in through that location. So it's getting expressed as sort of our climate zones because of these, major atmospheric cells that we're talking about here. Okay, so you got the low along there. Then, of course, that goes up, diverges aloft, right? And it begins to sink. Colder air as you go up vertical in the atmosphere, right? And so it begins to sink, and then you're sinking over the subtropic high zone in through there. And again, same thing down here on the southern hemisphere. And so you've got an area of high pressure, sinking air, subsiding air, warming everything, drying up any clouds, sort of thing. So our major deserts there. And of course the confluence there of those getting the trade winds happening Here we're having our westerlies happen in there, but then we got the 60 degrees, right? And then the 90 degrees with that high pressure again. So alternating pressure cells of low pressure, high pressure, low pressure, high pressure, way at the poles. And of course, it's sort of a mirrored image with the southern hemisphere as well. And this is really the idealized global circulation, kind of simple model of what's happening with these major pressure zones, okay, that we have. And really, it's all due to the unequal heating of the atmosphere, okay, in there. Some regions are getting more direct solar radiation, right? The poles are getting less, sort of thing. So it all kind of sets up because of that unequal heating of the land and the atmosphere as well. So those main pressure cells are the main kind of reason for the global kind of general atmospheric circulation. But we can get some things that will also influence these, can kind of disrupt that a little bit. And so we mentioned how land, the sort of a differential heating of land versus water. So we can get some influence from the continents as well. You can definitely get some seasonal temperature differences that will disrupt your idealized kind of global pressure pattern as well as wind patterns. Those will kind of shift seasonally as well. Because the continents, as you remember, the land will want to warm up more in the, the summer months, the more direct solar radiation. They will heat up faster into higher temperatures and cool down faster into lower temperatures than water will. Water will be more moderate. It takes a tremendous amount of energy to get that to increase in temperature. So your continents, yeah, you're going to have some seasonal fluctuations, those wide kind of temperature swings that you get seasonally over land, right? So, and of course it's most obvious in the northern hemisphere because that's our land hemisphere. Remember, the northern hemisphere has more land in it than the southern hemisphere, right? This is mostly the water hemisphere down here in the southern hemisphere. There's your land hemisphere, northern hemisphere. So we do see this more often in the northern hemisphere. It's more obvious there. And they'll kind of have a sort of a scenario of July versus January, seasonal changes happening, of maps that they'll show us. But we have a seasonal kind of change in wind direction called the monsoon. And so for that, I don't know, let me see if they've got the picture of it. Well, here's a couple pictures of it. A monsoon will be a change in the wind direction. So if you have the wind direction coming from the land out towards the water, that's going to be a drier scenario, right? Versus if you have the winds coming from the water toward the land, bringing the moisture-laden air from the coming off of above the ocean, that's going to create a lot of precipitation. So these monsoons are sort of seasonal changes in wind direction, making it come from ocean toward land. Going to give you your rains, tremendous amount of rains. And so let's look at the pressure and the winds directions for a January scenario. Here's your intertropical convergence zone. So that's sort of low pressure equatorial low, the ITCZ, intertropical convergence zone, they say. That's at, about the equator, so 0 degrees latitude all along here, okay? So in a January kind of scenario, we've got some winds here. So just notice where your high pressure system is, right around 30 degrees, right? These high pressure zones, about 30 degrees. This is January, north latitude, if we're just going to hone in on that. But notice here over Asia, India gets a lot of these monsoons, but in January, notice that there's high pressure over the land. The land is very cold, right, in January in the northern hemisphere. That's our winter solstice in the northern hemisphere. So your land's going to be very cold. So a high pressure sinking air, right, it's going to be over the land, and this will be divergent, so the winds are coming from the land out to the water. So no problem there. But look at the January scenario here coming next. We just kind of hone in over Asia and India there. We have major monsoons over there. So here's July now. So for July, if you remember, we're starting to get heating of the land, right, in the northern hemisphere, the Tropic of Cancer, right, you're getting your highest sun angles. So notice how those highs have kind of moved up, right? They've moved up a ways. And now look at your wind direction over Asia there. It's coming from the water towards the land, bringing that moisture-laden atmospheric moisture from the water over the land. And this will cause tremendous amount. Now you see a low pressure system there. Tremendous amount of precipitation. So it's like a reversal of the winds seasonally. A monsoon, and you get tremendous downpours of rain. Their rainy season. This becomes a huge problem because, yeah, it's coming in over the Himalayan mountains there, but it's kind of down in a valley, almost in a trough where that water can't get out. So they have tremendous amount of flooding, just a yearly cycle of this. We also do see that kind of out over our Rocky Mountain region. In the summertime, we do get a monsoon type of, just the rain will come because, yeah, it's coming in, you know, off of the water there, coming up over, and we'll get a monsoon as well in kind of over east of the Rocky Mountains. Here in the United States, we'll get a monsoon as well, but nothing like the monsoons that they see over in India and Bangladesh. Think of that. So a monsoon, it's occurring over the continents during warm months, so think of summer periods. Air is flowing onto the land, from water onto the land, so onshore. It's very warm and moist air from the ocean, bringing that moisture-laden atmosphere coming towards, so very buoyant, a good way to, you know, get the precipitation over there. Kind of a reversal then in the winter months, air flows off of the land. It's going to be very dry, or what we call continental air, very dry, coming from the land, much drier than from over the warm, moist ocean. So a monsoon, a seasonal reversal of winds, of wind direction with very large continents. So the influence of continents, especially over Asia. I would say the monsoons are very devastating seasonally. So a seasonal reversal of the winds, right, is a monsoon. Of course, that's going to bring precipitation as well. So think of Asia when you think of those monsoon scenarios. Okay, so yeah, that interruption of the land is going to have a factor, be a factor on our global circulation, that simple pattern we were looking at. So the westerlies, very much here in the United States, our weather patterns and our weather systems are driven by those westerlies. So they come from the west, that's the predominant direction from which it blows, from the west towards the east, and that is going to drive our weather systems right across the United States. It takes several days for those to go past, but that complex pattern there, or that simplifies pattern becomes complex because the airflow is interrupted by those cyclones, so sort of following one another, the low pressure following the high, low pressure, high kind of thing. So these cells in the northern hemisphere, because of the westerlies, they move west toward the east in the northern hemisphere. So in the United States, yeah, we always look out to the west. What kind of weather are they having out in the west? Because that weather is headed our ways in just a few days. It'll be making its way, you know, over to here in Arkansas. And it'll continue on out to the east coast as well. So always west to east here in the United States. But we've got anticyclonic and cyclonic flow happening along the way. So highs and lows kind of following one another. And the passive, the cyclones and the anticyclones are associated with the upper level flow. So the jet stream, that swift moving sort of stream of air, that geostrophic wind. So that's going to kind of be pushing it along and driving the flow of those systems across the United States. We can talk about some very local winds as well. These are produced by temperature differences, as you can imagine. They're very small scale winds. In a coastal kind of location where you're kind of an interface of the ocean and the land, we have something we call land and sea breezes. I think they give us a nice picture of this, but these are just localized differences in the heating from day to night. So here's the illustration of a sea breeze versus a land breeze. So panel A here, this first one, is going to be our sea breeze. But what's happening? Kind of on a summer day, you've got where the land is going to warm up much more quickly during the day, right? Warm land. That's going to cause the air to rise, right? Creating low pressure. Air will rise. It'll begin to cool. It's going to spread out. And then as it cools over the water, you've got sinking air, cooler air, right, over the water. And so it sets up a cell like this during the day, kind of in the summer months, to where you're going to get this cooler, and it feels really good. It's a sea breeze because it's coming off of that cooler water toward the land. So that's a sea breeze, okay, right there. Very refreshing on a summer day. Okay, so that's sort of the sea breeze scenario. But at night, right, your land is going to cool down a lot faster than your water is. So your land is cooler than your water. Okay, your water's still kind of warm from the heating of the day. Your land's going to cool down really rapidly. So that's going to create sort of a high pressure over the land and low pressure over the water. And so you're setting up a scenario like this, where you've got the wind coming from the land towards the water, and that's a land breeze at nighttime. So these are very local, kind of even a daily little bit of a cycle happening of a sea breeze and a land breeze. So sea breeze kind of in the warm summer months during daylight. A sea breeze was often going to bring in right along those coastal lands, kind of coming off the water up onto land. Very refreshing, okay, a sea breeze is. Another type, now they didn't give us a picture of it in your PowerPoints, but we do have a picture of it in your book on page 408. We've got figure 13.2, the mountain and the valley breezes. So again, little unequal heating of the land here, but sort of a local sort of thing, and a mountainous sort of terrain here. So during the day, the sides of the mountain are going to want to heat up more than the valley below, right? And so if that's heating up, you're getting the warm rising air like during the day, right? The mountain slopes are heated, the air rises, and that's actually going to bring up what we call a valley breeze, sort of that cooler sinking air towards the center, but the valley breeze coming from the valley up, because those slopes are getting heated up a little bit more, a valley breeze. Well, at night then, the air right up here above the mountain slopes is going to cool down very rapidly, right? And this time it's going to be going down towards the valley, right? Creating a mountain breeze. It's just a little reversal from day to night because of the unequal kind of heating and cooling that's happening on the slopes versus down in the valley. You can get a valley breeze, or you can get a mountain breeze as well. Kind of a reversal of those. Okay, a little localized kind of winds. So cooler air kind of draining down towards the valley in your mountain breeze. At night, though, for that one. Okay. Another one they talked about in the PowerPoint there was a Chinook, or the Santa Ana winds. Chinooks. So right here. This is a Native American term, a Chinook. It means snow eater. Kind of translates to snow eater. What happens with a Chinook is you're getting warm, dry airs being forced down the slopes. Let's think of the Rocky Mountains here. You kind of have that orographic lift of the Rocky Mountains, right? It's going to rain out on the windward side, but coming down the leeward side of the mountain range, so on the east of the Rocky Mountains, the leeward side, you've got compressional warming happen from that sinking air. So it's compressionally warming, right? Adiabatically warming. And so it's drying out everything that's very warm. It will basically melt your snow fairly rapidly. And so that's kind of like a snow eater or a Chinook. Just compressionally warmed air due to kind of a mountain terrain. The Santa Ana winds, think off to our west coast in California. Again, it's a kind of sinking air, compressionally warmed air, fast moving winds as well, and these can really exacerbate the fire dangers. They have a lot of those wildfires out there in California, but it's a very warm, fast moving, very dry air, and it will just kind of fuel the fires out there, those natural fires that they have. So that's what a Santa Ana wind is, and a Chinook. So kind of going down the mountain slopes, right, compressional warming. These will be very dry, warm winds, and they will like melt the snow kind of thing. So that's a Chinook, a snow eater kind of thing. Okay, we already showed you the sea breeze and the land breeze. They only had that picture for some reason in there. So how we go about now measuring our wind? Basic measurements. We want to know something about the direction of the wind and the speed of the wind. So direction becomes very, very important to us because, like I mentioned maybe before, that say we have a southerly wind flow here in Monticello or in Arkansas in general. If you have a southerly wind coming from the south, from which the wind blows, from the south. Well, down to our south, we have the Gulf of Mexico. This is going to be very warm, moisture-laden air, so humid and warm air. That's what it's bringing. What's to the south of us. And so a direction can really tell us something about the type of air mass that we're going to be getting, temperature and moisture kind of factors. A northerly wind, so wind coming from the north, so to our north, whoa, what do we got? We got Canada, we got the Arctic, so colder and drier air coming from the north. Yeah, that's going to set up some very high kind of pressure systems from there, cooler air, drier air coming along from if we had a northerly kind of wind. And so wind direction becomes very, very important in helping us to kind of do some forecasting meteorologically. So direction, winds are labeled from where they originate. So from which they blow, that's your wind direction. Not which way it's going, from which it blows. That's how we do a wind direction. For example, a north wind blows from the north towards the south, right? So a west wind blows from the west to the east. This is how you do your directions for the wind. It's not which way the wind is blowing, not where it's going to, it's where it's coming from. That's how we do a wind direction. Instrument for measuring wind direction is a wind vane. I don't know, I kind of brought a little wind vane. Maybe you've seen these, I don't know, on the tops of houses or something like that. A lot of times I have a little rooster on them or something like that, but then it'll kind of, you know, whatever way the wind's kind of blowing, right? A little arrow here. It'll give you a wind direction. That's one way. You can also, they kind of look like a sock kind of thing out by airports. You'll see wind directions with a sock kind of looking thing, another wind vane, to measure the direction from which the wind is blowing. Okay. They can also use they use compass direction, so we think of north, northeast wind, that sort of thing. But a scale from 0 to 360, so think of 0 degrees as being north, a north wind. 90 degrees would be an east wind, etc. coming on around. 180, a south wind. 270, a west wind, and so forth. So you can think of it as a circle, and there's 360 degrees in that circle. And so they can use a scale like that as well for wind direction. If we say that the prevailing wind is actually a wind that comes mostly from a particular direction, from one direction. So prevailing winds of the westerlies are from the west, right? So the westerlies, the prevailing wind is coming from that one direction. For wind speed, okay, we want to measure using an anemometer. So it usually has little cupped kind of shaped instruments, and so as the wind's coming around, right, this will go up or down, and we can kind of figure out a wind speed. There's a scale on here as well, but that's a cup anemometer, they call that, and we can figure out wind speeds from this as well. So that wind direction and wind speed. And changes in wind direction become really important. Of course, they are associated with the location of our cyclones and our anticyclones, right? Because we got all that circulation happening, right? The clockwise around our anticyclones and the counterclockwise around our cyclones or our low pressure. So they're going to kind of be replacing one another. And so they will be bringing along with them changes in temperature conditions. Remember, like a southerly flow, you're going to get your warmer weather here, and moisture conditions as well. Southerly flow again is going to be bringing more moisture. A northerly flow here in our parts would be bringing us a drier and cooler air mass. And so definitely you're going to get changes with wind direction. It becomes very important element of weather is your wind direction, right? And of course the winds are brought about by those pressure differences along Earth's surface. So wind measurement, a very important weather element. Okay, so that does bring us to the end of chapter 3, and hopefully that is a lot of information, so you may need to review some of this and certainly ask me any questions if you need to on this, but that does bring in all those different forces that come together to bring our atmosphere in motion. And so it is a three-dimensional, atmosphere. And so lots of forces coming together, pressure gradient force, Coriolis effect, friction as well, that sets up the various pressure cells due to the unequal heating of Earth's surface. So that will conclude chapter 13, and in chapter 14 we're going to take a look at weather patterns. Those low and high pressure systems coming along, creating some weather patterns, the various air masses that we do see. And so we're going to go into maybe a little more of the severe weather patterns, looking at tornadoes and hurricanes in chapter 14 as we continue a detailed look at the atmosphere. So I'll see you next time. Thank you.